Hello and welcome back to ECE484, Fall 2021. First I should mention that I posted on Learn that this revised evaluation scheme for the course is official. So essentially, if the original marking scheme is the best for you, you will be evaluated using that scheme. If instead you're better off getting a kind of a 5% boost in the lab weight and a 5% reduction in the exam weight, that's the scheme that will be used for you, okay? So I didn't hear any objections to that, so I've made that change. Okay, so we are at the very end of the course. We've started the final section we're going to be able to do. We are talking about state space control design for discrete time systems, okay? We're not going to cover all the material in this chapter. Like I said, this will be the last section that we do. So let's remind ourselves what we've been up to. So we started off with the basic problem, which is a stabilization problem. So we looked at our discrete time system, which might be obtained through discretizing a continuous time system, okay? And we want to stabilize it in the sense that we want to look for a state feedback, u equal to f times x. So what this means is that we're going to take each state variable and we're going to multiply it by a constant gain, which is the entry of that F matrix, and then we're going to use that to generate a control signal U. This is not our last lecture. We have one more on Tuesday. So yeah, 36 lectures in a course, so 36 hours. I mean, we'll see. If we finish today, we finish today, but I don't think we will. Okay, so we take this controller and we plug it in. This is the system we get. And what we want in the stabilization problem is that for that resulting system to be asymptotically stable, which remember, that means that no matter what initial condition you have for the plant, it should go to zero, right? Zero being kind of our desired equilibrium. Think of it that way, right? We've linearized our system at this equilibrium, okay? In other words, we want this matrix, A plus BF, to have no unstable eigenvalues, i.e. no eigenvalues whose magnitude is greater than or equal to 1. Okay. To solve this problem, we talked about controllability 2 lectures ago. And last class, we said, turns out that this controllability notion, which originally was presented as a notion of reachability, can you reach all the states, is equivalent to saying that the eigenvalues of this matrix can be arbitrarily assigned by suitable choice of the feedback F. Okay? So that's great because that, in terms of our stabilization problem, it means that if AB is controllable, we can compute an F so that the closed loop system has no unstable eigenvalues. Okay? We did an example of that calculation last class, and you should definitely review that example. Okay. Of course, if we're just trying to solve a stabilization problem, we don't actually need to be able to move all of the eigenvalues of the open loop system, right? The open loop system is just A. What we really want to do is we want it so that we want to change the unstable eigenvalues of A, right? The stable ones we can live with. And so that led to this related notion of stabilizability. And basically it says that our original problem of stabilizing this system is solvable if and only if what we said is that the pair AB was stabilizable, but what it means is that every unstable eigenvalue of A is controllable, i.e. you can actually move those, so you can get out of that unstable region, okay? And we have a test for that, and basically it's the PBH test. You check the rank of this matrix, but you only need to check it for the unstable eigenvalues of A, right? For controllability, this has to hold for every eigenvalue of A. For stabilizability, it's just the unstable eigenvalues. And again, we did an example of computing a state feedback in the case when AB is stabilizable but not controllable. Okay. But then we started saying, well, this is not realistic, right? I don't have a sensor for every state. It's very unlikely that you have it. And even if you could get it, you wouldn't want to pay for all those sensors. So we would like to just use this information that is actually available to us, right? What sensors do we actually have, and use those in our feedback. And that led us to this discussion about the output stabilization problem, okay? And so I'll remind you sort of where we left off. This is sort of where we left off. We're going to have our plant over here, our controller over here, and we want to design a controller which doesn't use the entire state, but just uses the information available from Y. so that the closed loop system is stable. So one way to state this is that given a plant model, A, B, C, D, we want to find a state space controller, AC, BC, CC, DC, so that the closed loop system is internally stable. Okay, that's the problem we want to solve. I remind you of what internal stability was. We talked about it in chapter 6. What it means is that no matter where you initialize the plant, no matter where you initialize the controller, both systems converge to 0. Like the plant state goes to 0 and the controller state goes to 0. All right? We discussed this in chapter 6. We're just using this notion of internal stability that we had from chapter 6. Okay, so we want to solve this problem today. That's what we're going to do today. And as I mentioned last class, what we're going to do is we're going to introduce something called an observer. And the basic idea is we're going to use this observer to estimate the state of the plant using only the input-output data, and then use that estimate as if it were the actual state of the plant, and use that to control our system. And we're going to see that that's actually going to work out quite nicely. Okay, so first thing we need to do is we need to estimate the plant state. So that's where the notion of an observer comes in. Okay, so we're given a plant. And what we want to do is design a state estimator for it. And we're going to call this an observer. Given a plant, an observer is another dynamical system which reads the input-output data of the plant. Right, the stuff that is actually available to us. The inputs are available to us on our computer because we pick the inputs. The outputs are available because the reason we're calling them outputs is because we have sensors on them. Right? It's modeling the information available to us through feedback. Okay? So this dynamical system is connected like this. Like so. Okay, and then I'm going to just pull a figure from the notes. And then we'll talk about the connection. Okay, so there's our plant up here. And the observer, what it's going to do is it's going to look at the inputs going into the plant, which of course we have because that's on our computer, measure the outputs of the plant, and use that information, along with our model of the plant, to come up with this variable, which we'll call x hat, as the estimate of the plant's internal state. Okay? And again, looking ahead, what we're going to do is we're going to use that estimate in our control to implement the state feedback from the previous section. Okay? So it's connected like this, and it has the property property that the difference between the plant state and this x hat state should go to 0 no matter what. In other words, that the limit as k goes to infinity of the difference between the plant's state minus this estimated state, that should go to 0 for every initial condition. Okay, so let's look at the picture again. So no matter how you no matter how you initialize this plant, or no matter how the plant is initialized, no matter how you initialize this observer of yours that you're going to design, we want that the difference between the plant's actual state, so x, and the thing coming out of our observer, this estimate x hat, that difference should go to 0. Okay? So in other words, x hat of k is an estimate of the plant state x of k at time k, constructed from input-output data. And the plant model. Right, so one of the assumptions here is that we have a reasonable model of our plant, A, B, C, D. Okay, so this observer is going to run on our computer. We can make it anything we want. Right? It's ours to design. It's not a physical system. It's what we are designing in order to solve a control problem. Right? So the physical system is embedded here in the plant model. Right? It's been discretized, but it's there. This is something we get to pick. So there's a lot of freedom here as to what we can choose. Okay? And so I'm going to argue that there's sort of an intuitive or natural choice, and it's kind of the standard choice for an observer. Okay, so let's figure out what we should use for that observer. Like suppose then that at time step k, we have some estimate x hat. Our observer has produced the estimate x hat of k. Well, if we're estimating the state to be x hat of k, that means that our estimated output is, so this means estimated plant output is, let's call it y hat. Right? I mean, of course, our observer has access to y, but if at any moment in time we've estimated x hat, what that estimate is saying is that our estimated output is this value. Right? And so notice that our estimated output depends on our estimated state and the actual input, because that's something we have access to. We have I/O data. Okay, but of course we also have access to the actual plant output. That's what our sensors are providing. And so in some sense, the difference between the measured plant output and the estimated plant output, that's sort of a measure of how far off, in some sense, our state estimate is. And we're going to use that, right? We're going to look at the difference between the measured plant output and this estimated output, and we're going to use that to inform the update rule for our observer. Okay, so this is at time step k. So now, if you have this information, what do you choose to be your next estimate? Right? This is something we get to decide. It's our decision, it's our design. So we need to pick a rule. We now need to pick a rule to update our state estimate at the next time step. So at time step k plus 1. Okay. And so I'm going to argue at this point, I'm going to basically write it down, but this could be anything, right? It's up to the designer what they want to use for this observer. But I'm going to argue that an intuitive and natural choice is the following. At the next time step, what we'll do for our observer is, remember, we have the plant model. So what we'll do is we'll put a copy of the plant right? But now written in terms of our estimate x hat. And then we're going to update based on the error between the measured output y and this estimated output. And I'll make it proportional to that error, so just linear. So I'm going to write this as plus some gain L times the difference between the estimated plant output and our actual plant output. Okay, so let me write down kind of the way to think about this proposed observer. This is a copy of the plant model. And this is correction term. You can think of this as a correction term. That is proportional to output estimation error. Okay, so notice what happens when our estimate x hat is actually equal to x, right? So imagine that time step k, our estimate was perfect. What would happen in that case? Well, this output error would be 0, so this term would go away. Again, we're assuming we have 0 error, so this is actually x now. And so we will get perfect estimate at the next time step because we have this copy of the plant model. So if x is equal to x hat, this goes away, and our update to the next time step for our estimate is going to give us the plant model, or the plant state, because again, A and B are assumed known. Okay, so that's why I'm arguing this is sort of an intuitive choice. Now it's not clear yet that it's going to work, but this at least has the ingredients to seem that it might work. Okay. Now in terms of L is really the only thing that's not defined by the plant model, right? That's the only thing that we're introducing. So L is our choice. That's the kind of the design parameter. And so in general, L will depend on the number of outputs and states. So it's going to be N, the number of states, by P, the number of measured outputs, right? The dimension of Y. Okay, and this is our gain. That's the only thing that isn't fixed in some sense by the plant model. Okay, so my argument is this is sort of an intuitive or like a simplistic kind of way of thinking about this observer or decision. You could have chosen anything here, right? This is our choice, but let's try this one and see if it works. So the question then becomes, does this proposed observer actually asymptotically estimate the plant's state right? Because remember, that's what we want. If we go back to our problem, I can pick that observer to be anything, but what I want is that the difference between the plant's actual state, x, and this estimated state, that should go to 0. And so the question is, does that actually happen? And asymptotically meaning as time advances. Okay, well, we have the tools to answer this question. So let's do it. So why don't we look at the estimation error, the difference between the plant state and the actual state. Okay, we'll call this the estimation error. And what we want is that this estimation error should go to 0 in the limit right? That means that our estimated state x hat has gone towards x, okay? So we know how to evaluate stability of dynamical systems, discrete time dynamical systems, right? We're going to look at the difference equation governing the evolution of the estimation error, and then we're going to check if it's stable, or design L so that it's stable, really. So let's see. Then, what do we have? E plus equals, right? The update to the estimation error is going to be x plus minus x hat plus, right? It's the next time step of x and x hat. But we know how the plant evolves over time, and we've proposed an observer, so we know how it evolves over time. So I'm just going to plug in those equations. So the plant state, the state equation, just evolves according to ax plus bu. Our observer evolves according to this choice that we've made. Okay, so I'm going to plug in, this is x plus, I'm going to plug in x plus into my equation down below. Okay, so we will get, a x hat plus bu plus L y hat minus y. Okay, so I just plugged in the expression for the next time step. Notice that we get a cancellation here. Okay, so I'm the next line, I'm not going to write the b's. The bu's are going to go away. So the effect of the input is now gone. And what I will plug in is the expressions for y hat and y in terms of x and u. Okay, so okay, so now I'll plug in y hat minus y. Now y hat is our estimated output, and it was given by c x hat plus du. And then the output y is the measured output, which is actually equal to c times the actual state x minus du. Again, we get a cancellation. And so we have, oops, I lost a term. Sorry, let me fix this. I lost the a times x hat. Okay. All right. So we have that. Let's simplify this a bit. So this is going to be equal to a x minus x hat. That's, remember, our estimation error. Minus LC x hat minus x. Let's write that in terms of the estimation error, E. So this is actually equal to E. This term is equal to negative E. So let's plug in E over here and negative E over here. And when you do that, you get this. Okay? So this linear plant and this observer that we've proposed, when you combine them, the estimation error, the state estimation error, in other words, the difference between the plant state and our estimated state, it will evolve over time according to the following difference equation. E plus equals sum matrix times E. We want that error to go to 0. We want our estimate to converge to the plant state. So what do we want? We want this system to be asymptotically stable. Okay? So conclusion. If we can design L so that this matrix, A plus LC, is stable, so if we can choose L so that A plus LC is stable, then E plus equal to A plus LCE is asymptotically stable, and our estimation error will go to 0 as k goes to infinity for any initial condition. In other words, for any initial value of our plant and any initial value of our observer. Okay? And this is what we want. So the problem then of estimating the plant state boils down to designing or choosing this L so that A plus LC is stable. A comes from the plant model, C comes from the plant model. You just need to figure out what L should be. Okay? So again, our proposed observer is given by, right? So if we plug in the expressions for y and y hat from above, it's the following. Okay, so again, all I've done here is I've plugged in this equation up here, I've plugged in the expression for y hat. That's it. I just plugged in y hat. Okay, and this is what our proposed observer looks like. And again, from a systemic point of view, this is just a system which measures u and y and produces an estimate x hat. Okay, so this is our proposed observer. And again, this runs on the computer. Okay, so again, the problem though, to make this observer work, we need to choose L so that A plus LC is stable. Okay, so again, let's figure out how we do that. So this will work if and only if A plus LC is stable. Okay. Now we did solve a stabilization problem earlier, but there the gain that we were designing, the F term, showed up after B. It was A plus B times F, the unknown gain. Here, L is showing up on the other side, if you will, of the plant model matrix. So what do? Well, we make the following observation. Observe that the eigenvalues of A plus LC, why am I talking about eigenvalues? Because we want A plus LC to be stable, right? So what does that mean? We want all its eigenvalues to have magnitude less than 1. And we observe that if I take the transpose of a matrix, that doesn't change its eigenvalues. Right? It's just swapping rows and columns. It does not change the eigenvalues. Okay? let's write out that transpose. So when you distribute the transpose, A gets transpose, and then LC transpose, you just change the order, right? L and C. When you take their transpose, their orders change. Okay, but now this kind of looks like the sort of problem we were looking at before yesterday. We have some square matrix plus some generally tall matrix times an unknown gain. And we want to choose that unknown gain so that the matrix has all its eigenvalues less than 1. This is exactly the problem we solved last time. So by our results on controllability, in particular on the results of the stabilization problem, we can conclude what? That we can, the eigenvalues of A plus LC can be arbitrarily assigned by suitable choice of L if and only if, again, looking at this expression above, we need that the pair A transpose C transpose be controllable. Okay, because again, by what we saw last class, if A transpose C transpose are controllable, I can figure out an L transpose to make those eigenvalues anything I want, and that means I can make these eigenvalues anything I want because they're the same eigenvalues. Okay. Similarly, there exists a gain L so that A plus LC is stable if and only if A transpose C transpose is stabilizable. Okay. And so we can use our same design procedures from last class to design this observer gain L. Okay, so let's do an example. Observer design. Okay, and we're going to design an observer for this double integrator system, which we've talked about quite a bit in this chapter. So, for the double integrator. Okay, so I'll remind you of the plant model. T here is the sampling period, and the output is x1. Okay, D matrix is 0. So here's our plant model. Right, that's where we're getting A, B, C, D from. Okay, so we seek a gain. When we talk about observer design, what are we saying? We want to design a gain L so that A plus LC is stable. So we seek a gain matrix L Now L in this case, remember, it's the number of rows equals the number of states, and there's 2 states here, so it's going to be two rows, and the number of columns equals the number of outputs. In this case, there's just 1 output, so it's going to be 2 by 1. So that A plus LC is stable, and if we can find such a gain, then we implement our observer like so, right? That's our observer. Yeah. So we want to design this L. So the question, this is very similar to what we did last class. Does such an L exist? Well, let's check this. Use the observation that we had above. Does such an L exist? Well, let's check if A transpose C transpose is controllable. Okay, if that pair is controllable, then definitely we can find an L so that A plus LC is stable, because we can place the eigenvalues arbitrarily. If it's not controllable, it may still be possible to solve the problem, but then we'd have to check stabilizability of A transpose C transpose. So let's first check controllability. And so remember, our test was that we would check the rank of B, was what we were saying before, but the role of B is being played by C transpose here. So it's going to be the rank of C transpose. The next part of this matrix, the controllability matrix, before was A times B, okay? But now the role of A is being played by A transpose, and the role of B is being played by C transpose. So I'm going to write that as, oops. And we stop there because there are only 2 states, so n is equal to 2. Okay, fill in the numerical values. So let me just scroll up a bit so you can see. So C transpose is going to be 1, 0. Okay, so you take the row vector, it becomes a column vector. A transpose is going to be in the first column will be 1t, and in the second column will be 0, 1. Okay, and so when we multiply that matrix times C transpose, we will get 1t, the first column. Okay, you can see that these columns are linearly independent. Also, you can see that the determinant of this matrix is equal to t, the sampling period, so it's not 0. And so this rank is equal to 2. So the eigenvalues of A plus LC can be freely assigned. Okay. Which means that our observer is going to work for this system. Right? We just have to pick L so that A plus LC is stable. So 2, design L. Okay, so let's write out, for now, let's write out what A plus LC looks like. So that they don't look like ones, I'll use little l, script L, for the first component of the L matrix, and little l, script L2 for the second component, times C. Okay. Multiplying this out. We get this. Okay. And so now the idea is I want to pick values of little l1 and little l2 so that this matrix is stable. Okay? And not only can the easiest way to do this, or the principled way to do this, is to pick desired eigenvalues for this matrix and then solve for the corresponding gains. Okay? Little l1, little l2. Okay? So the eigenvalues of this matrix are the roots of this polynomial. Oh, did I make a mistake? I did make a mistake. Sorry about that. Yes, that should be correct, I believe. Okay, sorry about that. Minus L2. How does L2 move from the left side of the matrix to the right? Oh, yeah, that's a good point. That's right. That's not right. Okay, I've got this. This is completely wrong. Thank you. So I made a mistake. This should be this. Good point. Okay, let's do that again. This is 1t. Okay. Thank you for that. This is 1t. And now add these together. Okay, yeah, good point. And so, okay, yes, consistent. Minus 1, z minus t. Okay. So, okay, multiplying this out, you get the following. And so I want to make sure that that polynomial is sure. In other words, the roots of that polynomial are all magnitude less than 1. And so, I mean, I could just pick random, I mean, what I will do here is I will pick two desired eigenvalues to generate a desired polynomial and then compare coefficients. So in this case, because it's an observer, it runs on the computer. There's sort of no limitations. I don't have to worry about actuator constraints in this case, right? So I can actually make my response really fast if I want. And that means that my estimate is going to go towards the state estimate really quick, right? You know, we've seen in pole placement, when you place your poles too far to the right in continuous time or too close to the origin in discrete time, it can result in large control signals. But here I'm not worried about control signals because I'm just doing an estimation problem, right? I'm just trying to estimate the states variables. And so I'm going to pick my poles in some sense to be fast, really fast, or my eigenvalues to be fast. I'll pick them to be at the origin. So I get a finite impulse response system, really quick response. So I'll pick my desired eigenvalues to both be 0. So that A plus LC is nilpotent, which we've seen in chapter 6. What does that mean? It means that after a few iterations, this matrix to some power is going to go to 0. In fact, this matrix to the power of 2 will be 0, which means that our estimation error will go to 0 after 2 time steps. So that x hat of k, our estimate, equals x of k after a finite number of steps. In this case, that finite number will be 2 or less because of the size of the state. So this is called a deadbeat response. Okay, so it's just a choice of desired eigenvalues. I'm going to pick them to be 0. So my desired polynomial is just z squared. So the design problem is choose little l1, little l2, so that these coefficients are both 0. So equating coefficients, yields, hopefully I didn't make a mistake here, L1 equal to -2, L2 e to -1 over t, and our observer gain. Okay, that's our observer gain. Finally, our observer to be implemented is given by x hat plus, I'm just going to rewrite the equation and then I'll plug in the specific data. In this case, the plant had no D matrix, so there's no D terms showing up in my observer. And in detail, what it will look like, I'll write it down here. So that first matrix is A plus LC, second matrix is B minus RL. Okay, so this is our observer, and if we want to draw a block diagram, it looks like so. Okay, so that's the code that you would run on the computer, and you'd measure the output or the input going to the plant, the output coming out of the plant, and after, in this case, a finite number of steps, this estimate should be hat. This estimate would converge to the plant state. Okay, so that's observer design. It's really leveraging what we did for our controllability stuff or stabilization stuff. Okay, and again, looking ahead, what we'll do is we'll take this estimated state, x hat, and we will use it in our state feedbacks from earlier. Right, so we've effectively solved the problem of some sense of the fact that we do not have sensors for all of the states. Right, so instead of having sensors for all the states, we'll just estimate their values. Okay, it's left to be shown that this is actually going to work, but that's the basic idea. Okay, so that's the key idea here. A little bit of terminology, and that'll be we'll wrap up for today. So we're going to call the pair CA observable. When you can place the eigenvalues of A plus LC any way you want, i.e. if this transposed version is controllable. Okay, and if you take the controllability matrix of this pair and you take the transpose of it, you'll get what is called the observability matrix. If we define W sub O for observability now, to be this matrix, so C Okay, so what is this matrix? It is the transpose of the controllability matrix of this guy. It's called the observability matrix. I'll have to stop there. Then we're going to say that the pair, a test for CA being observable is that WO have rank n. Okay, I'll just write that and I'll stop. Then CA is observable if and only if the rank of WO equals n. So observability, like controllability, boils down to a rank test. Okay, so we'll stop there. We'll see you guys for the last time on Tuesday. I'll stick around if there are any questions, but otherwise I will see you then. Good luck on the remaining parts of the lab.